So now that we have these updated coordination spheres, right, these higher coordination numbers, we actually end up with new options for isomerism when we're drawing out these structures. So first we're going to talk about the isomers of octahedral-based complexes, and then we'll talk about some of the kind of oddities of the five-coordinate complex. And we're going to explore the five-coordinate complex in greater detail in class. So after the first quiz, I want you all to definitely practice drawing out more octahedral complexes. Some of your pictures were very clear. Some of them needed a little bit of work. The nice thing with an octahedral complex is we can actually just draw our three-dimensional axes if we would like to represent the octahedron, right? And so there's 6 different positions here that we could have our ligands on. And we notice if we draw these axes and draw them carefully like they are the x, y, and z axis, we actually don't really need to use dashes and wedges to clearly convey that three-dimensional structure. We definitely still can, but we don't have to. The other way of drawing an octahedral complex is that you draw the straight up and straight down, the axial type positions. You would draw a few wedges to stick out of the plane and some dashes. Now, this is, again, just another way that you can draw an octahedral complex. It's entirely up to you. But now if we're talking about the isomerism, right, the relationship of these ligands around an octahedral complex, what we're trying to do is describe the relative positioning, right, their relative positioning. And this is something we talked about a little bit in the lab, and you will get more practice with this as you're working with Avogadro in creating these three-dimensional structures. So when we are talking about the relationship of two ligands, right? Or if we have two ligands, we're trying to describe the relationship, we can use either cis or trans. And so this relates back to, the kind of terminology we're used to in organic chemistry. So cis are these positions on an octahedral complex that are right next to each other, right? So these would be considered cis to each other. Whereas the positions on the opposite side of the ring, right? So if I describe like the one that's pointed straight up and straight down, these are the trans positions on the ring. And so again, this is just a way of describing the relationship between the location of two ligands on an octahedral complex. Now, if we're going to be talking about three coordinates, right? So 3 ligands here, we have FAC or MER. And this is the facial isomer and meridional isomer, right? The facial and the meridional isomer. And so these again are describing the location of 3 ligands on our given complex. So if they form the face of the octahedron, right? So octahedron comes from an 8-faced object. So if we connect these 3 ligands and they form the face of an octahedron, this is our facial isomer. However, if we were going to connect our ligands, and this face that's generated by connecting these 3 ligands includes a line that goes through our central atom, this would be considered a meridional isomer. All right, and we kind of saw these in the lab, and we will get more practice with these. They're much easier to see if you draw out like the three-dimensional figure, especially if you're using Avogadro. So here we have the 2 different ways that we can describe isomers of octahedral complex. Now let's talk about our 5-coordinate complex. And so as I talked about in one of our previous discussions, when we have a 5-coordinate complex, right, the one at least that we are specifically going to be talking about right now is our trigonal bipyramidal system. And so the reason we start with this is that this is our sterically favored 5-coordinate complex. So without a strong electronic driving force, this is going to be our lowest energy conformation. And there are 2 different positions here. So we have axial positions, and we have our equatorial positions. Hopefully this isn't causing too much of a flashback to chair structures. in organic chemistry, we aren't going to be thinking about these as chairs at all. Axial just means it's lying along essentially our z-axis here. And equatorial, think like the equator around the Earth. So these are the ones that, circumnavigate our metal complex. And these positions are not equivalent, right? So these are not equivalent, meaning we will have a set of bond lengths for our axial positions, and we'll have a set of bond lengths for our equatorial positions, and they are not going to be the same. So generally, the axial positions are longer bonds, right? So generally, axial is longer bonds, right? This isn't always true, but it's generally true, and even if it's only a small amount. So if we look at something like PF5. The axial bond lengths here are 1.57 angstroms, and our equatorial bond lengths are about 1.53 angstroms. And if we have a structure where we have a mixed set of ligands, right? So if we are looking at, let's say we had one fluorine and the rest of these were chlorines. What we would do is we would arrange our system to where our most electronegative ligand goes in an axial position. And so this is an application of Bent's rule that is actually kind of behind a number of things that you might have been seeing all the way back through Gen Chem, but maybe you didn't know that that's what you were really seeing when you saw them in Gen Chem. So whenever we have the option, we want to put our most electronegative atom in our axial position. And we're going to see an application of this actually in our next video where we talk about how these isomers can interconvert, right? It's not quite as complicated as like a chair flip from organic chemistry, but these isomers are not necessarily static. So these can rearrange, we can actually get switches between axial and equatorial positions, and we'll talk about that in a little bit. Right, so again, we want to be able to apply Bent's rule that the lowest energy conformation would have the more electronegative in these axial positions. And we also want to know that axial and equatorial are not equivalent positions when it comes to these 5 coordinate complexes. Right, so we'll kind of come back to this in just a minute when we talk about fluxional shifts.